I didn't mention that ahead of time. So yeah, starting the session. In terms of how the meeting's going to flow, like I mentioned, we're going to go over a quick overview of these two papers. Then towards the end, we'll have a Q&A session. For the Q&A, we typically use an Excel. I'll drop it on chat. Feel free to start asking your questions on the Excel. And note that folks who ask questions will get the notes that I made for the session, which contains a lot more details and a lot more important takeaways. Definitely, we'll discuss them during the session, but it's a good thing to have handy for yourself as well. Just sharing my screen. Let me know when you guys can see it. Cool. Welcome all to BuildML's third research hangout. This time we're going to be talking about ML tech depth and production readiness. Just let me know in the chat if these slides are visible. Hopefully they're visible. Just letting a few more people in. So what exactly is BuildML? We're essentially a free community for everyone to join with the aim of building a long-lasting and fulfilling career in data science. So we do weekly research hangouts that are already live. We have monthly project builds. One starting in October, it's going to be a recommender systems project. Kaggle has this project called H&M Fashion Dataset that's going to be the recommender system that we're going to be building out throughout the month of October. Each week, we'll have sessions talking about how to do data analysis, feature engineering, how to build your baselines, choose your metrics, build out a simple model, all of those good stuff. So if in case you're looking to build products out for your portfolio to transition into data science, or just to get familiar with the advances in data science, it's a good series of sessions to be a part of. We'll also have a group chat so that you can ask questions and sort of use it sort of like a Kaggle discussion board as well. And we also have study groups just to make sure that your foundations are always solid in the sense that myself included, when I started out with data science, I would say I initially jumped directly into tree-based models, and I actually skipped over linear and inverse regression completely. And it was a while later I started reading this book called Introduction to Statistical Learning in Python. Sorry, at that time, Introduction to Statistical Learning in R. And then I sort of learned the foundations of those models, which you technically should learn first. So yeah, I feel like a lot of people may sort of do that, and hopefully the study groups will help clean up the foundations. We're going to be launching study groups starting November. So do make sure to follow us on all our handles. I'll post them in the chat. Um, our LinkedIn handle is fairly active. Instagram and YouTube handles are sort of coming up. I saw in the comment that I'm not audible. Let me know if I'm actually audible in the chat. Cool. Okay. Okay. I'm assuming it's just a problem for one person. Ashutosh, feel free to drop and rejoin in case you can't hear. Cool. Coming into today's agenda, so we'll start with how you go about reading papers. There is a bit of a trick to it, something that I picked up during my master's, in the sense that you don't need to bang your head against the wall trying to understand each and every aspect of the paper. So there's a bit of a framework that I picked up, and I feel like could be useful for a lot of folks. The next is we'll go into the problem and the proposed solution of these two papers, the tech debt paper and the production readiness paper. Both the papers sort of align pretty well, and the main authors are about the same on both papers. Then we'll go into sort of the research space surrounding ML productionalization, essentially. We'll talk about what technical debt is. We'll talk about how to get a ML product to be production ready. And then we'll have a discussion. Hopefully, you guys will have a couple of questions, like I mentioned, drop it in the Excel. And for folks who actually ask questions, I'll send over my notes for this session. It has like key takeaways that you can hopefully take and implement in your day-to-day as a data scientist, data analyst, etc. Starting with how to read papers. So typically, I always use this sort of phased approach for reading papers. Mostly because if you take a paper and if you try to read it from start to finish, it's often hard to understand or digest. You sort of get tired in between. It depends upon a lot of prior work that's sort of hard to understand as well when you sit and try to read through the paper in one shot. So this phased approach has been working fairly well for me. So usually you skim the paper and try to understand the problem and proposed solution. So the abstract, introduction, and conclusion, these are the only three sections you read, and you try to understand what problem the paper is trying to solve and how they're trying to solve it. This is also a good point that if you feel like this paper isn't for you, in the sense that the paper doesn't add a lot of value to your life as sort of a day-to-day life of a data scientist, you can drop that paper right then and there. That's typically the approach I take almost every Sunday. I pick up like a few papers from a few of the content creators that I like, and I try to read their problem and propose solutions, see if it actually resonates with my work or what I am interested in. And if it does, I keep the paper to read for the next of the week. If it doesn't, I drop it then and there. The next idea, the next phase, which can be done on another day, is sort of understanding the research space. So it's usually the related work section that's typically found in the first few pages or towards the end as well nowadays. So your paper might depend upon or build upon the work of prior researchers. So that's a good way to sort of understand or develop a mental map of what all has been done in the field and what you need to be aware of. The main things you need to be aware of is like the metrics that are used, the benchmark data sets that are often repeated across papers, and sort of like the semi-SOTA baselines you need to compare your solution to if in case you're going to be developing something in that space. Um, for instance, if you're doing something like forecasting, M5 is a benchmark data set that that you need to be aware of. Metrics in forecasting like MATE, SMATE, etc. are metrics that you need to be aware of in specific to forecasting. And in terms of like um, uh, um, um, benchmark models. There are quite a few deep AR, deep and basic statistical models like ARIMA and SARIMA. If you can actually scale it, also work fairly good. So understanding or having this mental map of okay metrics, benchmark data sets and benchmark models will help you understand the space and evaluate the research a bit better. So use ChatGPT heavily, go through related work, try to develop that mental map, and that's the only sort of goal with the second phase. So typically like Monday, Tuesday, I spend some time understanding the research space and try to develop this mental map for whatever paper I'm reading. And it definitely gets easier like if you stick to one domain. Like I stick to mostly recommended systems, so I have a decent idea about the metrics, benchmark data sets, and SOTA models in that field. So as you go along in a particular space, it definitely improves that, and the time you take to understand the research space definitely goes down. The next phase is primarily to understand the approach and the results. So um, primarily here, you try to figure out what novelty in the approach exists for whatever is proposed in the paper and what kind of results they got. Here, you're again trying to see if they're using standard evaluation patterns, in the sense that are they using the benchmark metrics or are they using some gimmick metrics to show improvement in some um, minuscule part of the model which may not actually be relevant. So are they using benchmark metrics? Are they using benchmark data sets, or are they just bringing up data sets of their own? And are they comparing it with standard models in that particular space? And are they how are they setting up the standard models? Because how you set up, how you hyperparameter tune those standard models can really impact the performance. Like if folks here had been part of the last session, we saw how the author kind of messed up on how he set up the standard model that he wanted to compare against, because of which he got sort of inflated results of how much better his approach is. And yeah, finally, the results, how much better is the proposed approach to what the standard approaches are? Is it statistically significant? And then finally, we spend some time critically analyzing the paper. Are they explaining why they went with this particular design decision of maybe like including some method like teacher forcing, or using custom attention heads, or using custom back propagation, like different techniques that they propose in the paper? Are they explaining why they're doing it? Do they have an explanation of why the model is better than whatever is existing thus far? Um, Especially in like DL research, this kind of explainability is lacking. So looking for that, trying to analyze if this is foundational work that you can sort of carry forward in your day-to-day as a data scientist would also help. And finally, discussing with peers. This is a great forum to do that. Sort of figure out what you like about the paper, what you didn't like about the paper, and what you wish the paper actually talked about, and how to sort of uh, have like practical takeaways from paper just by discussing with peers, hearing different opinions. That's a good way to learn. So this is typically how we approach reading a paper. Again, you don't need to read a ton of papers. Like 1 or 2 papers a week is that's applicable to your field, can really level up your knowledge and level up the kind of informed decisions that you can make in your day-to-day as a data scientist as well, in my opinion. Cool. Now coming to our paper at hand. So we had 2 papers in for this session today. One is the technical depth paper. The second is the production readiness paper. Both of these papers, what they're trying to solve for is the fact that machine learning systems, like large-scale productionized ML systems, they came out primarily post like late 2000s, and how people productionize them was very similar to how they productionize software products. Even though they're not technically software products, ML products have a very tight coupling between different elements, between like model and data, which typically you don't want in software products. You want to abstract everything out, you want to decouple. So since they approached ML productionization like they would software productionization, a lot of long-term maintenance issues came about. These long-term maintenance issues are typically what we call as technical depth in the field. So how do you actually resolve or account for these technical depths? That's what the first paper covers, and it provides a mitigation strategy for some of these technical depths. The second paper is actually the paper from Google, which goes over the production readiness checklist. Essentially, what does it take, or what all do you need to have in place to put an ML system in production? And they have a pretty decent checklist of, I think, around 30 to 32 things that you need to keep in mind. And it sort of has a very simplistic rubric of how to assess if your system is ready for production or not. So that's essentially the problem and solution. Going into the research space as well, these 2 papers form a very interesting um, foundational set of research in this space, I would say, primarily because um, typically when you're trying to understand research space, you're trying to understand previous papers that were seminal, that sort of define the space. In this space of like ML productionization, ML technical depth, etc., these 2 papers are actually what is the 2 seminal papers. So there is actually very little prior research that proved to be seminal in the space. So it's like starting with a clean state. You're starting in a research field where what you're reading is sort of the best thing that you can read. So these 2 papers, Hidden Technical Depth in ML, it was, I think, a Europe's fan favorite, and the ML test score from Google, the production readiness checklist. These 2 papers sort of form the foundation. So you can start with a blank slate. There's no prior research that you actually need to be aware of, which is pretty cool, I feel. And also a call out for these 2 papers. These aren't like your typical, like I mentioned, your typical machine learning modeling papers where you have a model, you have results, you compare it. These are more theoretical papers which provide guidelines of how to productionize ML systems. So it's also a very light read, and I feel like, especially this paper, has become sort of part of curriculum at multiple universities, including my own university. It was like a must read. So a really seminal work that we'll be discussing today. Um, and also apart from being seminal, really like common sense sort of work as well. Cool. Coming to technical debt, the first paper, the technical debt paper, like I mentioned earlier, technical debt is essentially when you have a system in production, the long-term maintenance costs of that system. Sometimes when you're moving fast, you don't build it out. Like you don't build for scale, you don't build for access restriction, you don't build for logging and debugging easily. A lot of those things you might drop the ball on when you're trying to move fast. So you might incur what we call as this might actually lead to more effort long term when maintaining the product. So whatever you skipped out on, which may increase the cost of maintenance in long term, is what we call as technical debt. So coming to the different kinds of technical debt that the first paper sort of introduces. The first one we call primarily the erosion of boundary technical debt. So there are like three main ones. The first three main ones within that category, the erosion of boundary technical debt category. The first one is called entanglement. This is primarily because the model and data are very tightly coupled. So if you change anything, you change everything. For example, if the input distribution, like one of the features, input distribution changes, it can lead to changes in the model performance. So how do you actually mitigate this, or how do you actually control for this when you're building a production system? One is drift detection. Drift detection is like making sure like I mentioned, the distribution in the input is sort of similar to what it was when you actually trained the model. So there are ways that you can sort of compare the distribution of, I mean, compare the divergence between two distributions, like a training distribution and testing distribution. So usually in production systems, you build out a monitoring tool and you make sure that the training distribution and the serve time or inference time distribution are somewhat similar, or they don't diverge by more than a certain amount that you sort of define. So drift detection is a good way to combat and like the entanglement issues that come up when you're building an ML solution where the model and the data are tightly coupled. Another way is building ensembles. In my opinion, you can build ensembles so that if in case like one feature's distribution sort of changes, that feature might be important to one model, it might not be as important to another model. And building ensembles could be a way of reducing the dependence or reducing the impact that changing one thing, one feature could have in the whole model. It could be a way, but in my opinion, it's not that um, uh, confident a way of accounting for entanglement. And in my opinion, it's always better to go for drift detection and monitoring and setting alerts on divergence in distribution rather than building ensembles. But both these methods are sort of recommended in the paper. The second one, the second type of depth in erosional boundaries is correction cascades. So in correction cascades, what happens is you have developed a model to solve a particular problem P. Now you want to solve a particular problem, maybe P dash. That's maybe like one step ahead of P. It could be something like you build a recommendation system where initially you build a candidate generation system. Now you want to show the products that a customer should buy maybe during Halloween. So what typically is done is you build a re-ranker on top of the candidate generation system, and then sort of re-rank whatever. Sorry, somebody got re-rank whatever items you want to show to the user based on the seasonal offers or something like seasonal offers or promotions, etc. So a re-ranker is a model sitting on top of another model which takes the input of the first model. So that's where correction cascades come in. The paper doesn't really the mitigation strategy that they provide is essentially building a completely separate model independent of the first model. In my opinion, correction cascades are fairly natural. and you don't need to necessarily mitigate for it. Monitor both the models that you're using, but I would say it's not something that you necessarily need to avoid, especially because like in recommender systems, it's fairly well established that models take the input of other models and sort of use that to fine tune the results. Bit of like a difference in opinion. Um, but yeah, definitely like use your own experience to sort of figure out if correction cascades needs to be mitigated or not. The next one is undeclared consumers. Very easy. Like people are using your ML output without you knowing, essentially. And the mitigation is very simple as well. Make sure that whatever outputs that you're providing has access restrictions on it. So if it's a batch prediction, you'll probably provide it in a table. Provide access. I mean, put access restriction on that table. If it's an inference, your output is hopefully going directly to the customer and it's getting logged, maybe in a logging table. Again, put access restrictions on that logging table so that not anybody can access those ML results. Primarily because if you provide open access to your ML results, more and more people will start using it. And you will create dependencies that you're not aware of. So if you create dependencies that you're not aware of, um, what happens is whenever you want to change a model, they will also get affected and they'll start raising issues that, hey, you changed the model, our behavior completely depended upon your model, even though we didn't let you know. So yeah, undeclared consumers are another thing that you need to watch out for and sort of mitigate for. The next one is data dependencies. Next set of dependencies, technical debt that you need to address is data dependencies. So within this, we have two. One is the unstable data dependency, and the other is the underutilized data dependency. Unstable is sort of very similar to the first one that we discussed in the sense of feature distribution or input distribution, in the sense that as time proceeds, the way your feature behaves might change, or the input distribution of that feature might change over time. So if you have any engineered features on that, you may need to recalibrate them. For instance, like term frequency, inverse document frequency for documents. Let's say you calculated during train time and then you're storing it and you're using it during serving time. In those cases, you may need to like as time proceeds, what the TF-IDF scores that you have may no longer be relevant. So you may need to create versioned copies, so that you can use those version copies for reproducibility. Like whenever you want to get the results or recreate the results that your model produced at timex, you can refer to that version copy, pull whatever engineered features you had and try and recreate the results of the model. It really helps in like making sure or understanding why the model behaved a certain way at a point in time, and it also helps in tracking, in the sense that um, sort of figuring out what changed over time, and when did you decide to reflect that change in your engineering pipeline. So yeah, unstable data dependencies is primarily about resolving them or mitigating them is primarily about versioning. And as long as you have like a strict versioning system and what we call like a feature store in place, you should be good. The next one is underutilized data dependencies. So in ML, there is like, especially when you're moving fast, there's a tendency to just take all the features, throw it at the model, and see what kind of performance you get, and maybe eliminate a few features, but not be very rigorous about the feature set that you're using. So because of this, you'll keep features that provide very minimal improvement to the model, and you may also keep features like features that are correlated, like two features are correlated. One of them actually influences the model. The other one doesn't necessarily. So you could actually trim it down to one single feature, but you keep both because you haven't done this proper elimination of features that aren't required. So yeah, the best way to mitigate for that underutilized data dependencies is to do rigorous trimming of the feature set almost every like quarter, I would say. So you use this leave one feature out evaluation, essentially removing one feature, seeing how the model performs. If the model performs about the same, then you remove that feature. If the performance drop is somewhat significant, what is significant? It depends upon your space. But if the drop is somewhat significant, you retain that feature, and you do that for every feature to sort of figure out what needs to be trimmed and what doesn't need to be trimmed. Depending upon the size of your feature set, you can change it from once a quarter to once a year as well. So that is the data dependent technical debt. These are again things that you need to keep in mind when you're releasing something into production. And like, even though we are covering the depth right now, towards the end we'll talk about the checklist of things that you need to keep in mind when you're releasing something into production. Coming to feedback loops. Feedback loops are primarily how your model may get influenced by its own output or output from other ML systems. So there are direct feedback loops, essentially things like, okay, let's say a recommender system provides a list of items that could be shown to the user. You eventually, the user might only go through the top 20 items. So the recommendations that the recommender systems provide act as, and within this 20 set of 20 items, the user may engage with some, the user may not engage with others. So if the recommender system provides a rank list of 20 items, these 20 items are what you're going to use to fine tune the recommender system again. So essentially, you're controlling the feedback set for the recommender system by what the recommender system is producing. So you're not providing an unbiased sort of feedback to the recommender system, which may cause the recommender system to index or enforce its own biases. Like, for instance, if a recommender system is sort of recommending a certain type of product, let's say Marvel movies on Netflix, and the user watches a few Marvel movies, then because yeah, just because like they're good movies, but um, the user might have been interested in something like true crime or fantasy, but within this top set of top 20 that you recommended, you didn't have any true crime or you didn't have any fantasy. You only had like a few Marvel movies, a few action, comedy, stuff like that. So now what happens is you don't get any positive signal that you need to recommend true crime or you need to recommend fantasy. You only have like this set of 20 that you expose to the user. And since they click the Marvel, the model will start to reinforce the fact that, hey, this user actually likes Marvel, so let's recommend more of content like this. So that's essentially the direct feedback loop. And how you combat for it is by randomization, injecting randomization, so that this set of 20 isn't just based on what is like finely tuned based on what you learn from other users or what's popular, but you may inject a few movies that the user could like, maybe they don't like, but you inject it just so that you provide an opportunity for other content to also become relevant. So that can be introduced by what we call banded methods, or it can be introduced by other methods as well. But the essential idea is inject randomization. The other way that models can be influenced is by hidden feedback loops. This is when a model output might depend upon other model outputs. A very common example for this is like in finance systems, how there are two systems that are doing trading. If one system changes its algorithm and trades in a different way, then the data in the market changes, which causes the other system to learn this changed pattern and behave differently as well. So these hidden feedback loops can also happen. It's when you have multiple ML systems that coexist in the same space, one can influence the other. So those kind of feedback loops also are something you need to keep in mind. And how you combat it, again, prediction drift detection. You sort of keep track of what your model is predicting, and you try and assess how those predictions change over time. Cool. Coming to the next portion, the ML systems anti-pattern technical depth. So, what exactly do we mean by anti-patterns? This usually happens again, like when you're moving fairly fast, when you have tight deadlines, you introduce a lot of code where you're like, okay, I'll code it out for now, I'll come back and fix it later, sort of mentality. Like these are these things we call blue code, and essentially you sort of write very patchy code to get things working, in the hopes that you'll have time later to sort of clean it out, like ways of how you import data, ways of how you create feature engineering. Like sklearn has a lot of functions to process your features, but you might create your own custom functions which may not be as performant. So sklearn has a common thing that we see is like sklearn has this pipeline function where you can put together everything in a neat pipeline, and process it one after another. But most people don't use it, and they sort of create like this patchy custom function where they call one function after another to process the data as well. It's not that readable, it's not that maintainable as well. Those things are things that happen, especially when like you're against tight deadlines. Another thing is very similar as pipeline jungles. Essentially, you have a lot of ETL. You keep on testing with different features, and over time, you have these multiple ETL pipelines running to create your feature set. There's a lot of repeated SQL. There is a lot of redundant SQL. Some of your SQL is not performant. So these pipeline jungles can also happen. Like it's essentially when you have like this 10 pipelines that were built over time. But if you knew that these were the features that were required, you could maybe develop like one or two clean, really efficient pipelines. So again, happens when you build stuff over time and you're not maybe thinking about refactoring the code, or you don't have time to refactor the code as you're developing them. So that's more of a side effect when you build products that are built over time. Then dead experimental code paths, again, as the name sort of declares, and so when you're trying out different things, you may comment code out, or you may create a function, but then later not use that function. Again, all of these three things can be sort of fixed by refactoring your code once in a while. Like when you're setting out the 1YP, the 1 year plan for your team, putting in some time to refactor the code for some of your projects is always good. And this is the best and sort of easiest way to deal with this depth. Like the paper does say that when you're developing, you should keep in mind these things. But when the road hits the rubber, I feel like it's okay to move as fast as you need to meet your deadlines. But always keep in mind that the refactoring has to be done. Keep it in maybe like one of your sprint tasks, or one of your Kanban boards, whatever you use for project tracking. And when you get the time, actually come back, revisit, and do the refactoring. The last one is abstraction depth and common smells. I would say this is kind of a bit of an overkill in terms of technical depth. So what they're saying is there aren't like proper interfaces for ML models, which isn't as true. Like if you're using PyTorch or TensorFlow, there are like some decent interfaces to represent models. And then they're saying there are certain common smells that are exist in code, like your data type should indicate what kind of data you're processing. But in ML, there are so many different types of data. Like even if you declare something as float, the value could be a log odds multiplier, or it could be a decision threshold value. So it's really hard to distinguish just based on the data type. And they say that ML needs a bit more functional data types and bit more functional interfaces. In my opinion, it's a bit of an overkill. And like at least in my day-to-day, I haven't focused as much on this type of technical. Cool. Coming to the next, and I think the last two types of technical depth. The first is configuration depth. It's a pretty simple depth. Essentially, like whenever you're building an ML system, you have different parameters that you want to try out. And this sort of helps you visualize or see all those parameters and edit these parameters whenever you want to. So that's essentially what a config file does, or if you're maintaining it via DB, what that config DB does. Whenever you want to change those parameters, you can easily change those parameters. And the mitigation is just to have like a config file or a good DB that you can edit easily, and not sort of hard code those config parameters into your code. Then dealing with changes in the external world, like we all know, like when you actually productionize a model and the data comes in live or batch predictions are run, your models might behave a bit more differently than what you saw in backtesting. Hopefully they don't. Like you're consider all the scenarios, and your backtesting and your online performance sort of matches very well. But there are certain things that you can keep in mind so that your models remain relevant for longer when exposed to the real world. And one is like fixed threshold in dynamic settings. Essentially, like if you have distant thresholds, sometimes we have a tendency to fix those threshold. Like if it's like a classifier, you fix it at zero point 0.9 and then sort of use that in code. But over time, maybe your distribution changes. Zero point 0.9 may not be that relevant anymore. So the mitigation that the author suggests is to define that threshold dynamically from the validation set. But in my opinion, it really depends upon the use case. Sometimes certain behaviors don't change, or if they change, it's essentially a fault of a failure of normal business process. So in those cases, I feel like a fixed threshold is also fine. So this is something like in my experience may or may not be something you want to actually address. Then there is monitoring and testing. Essentially, irrespective of whatever test cases you have, irrespective of how well you've designed your ML system, you have to have monitoring. Otherwise, when something fails, it's gonna take you a long time to figure out what went wrong, and maybe you may not even get alerted about the issue until it's like a day or 2 days late, by which business may have been impacted a decent amount. So um, make sure you have good monitoring and testing systems in place. Drift detection is like a good one. You make sure that the input isn't diverging too much, the output isn't diverging too much, and then you have guardrails. Essentially, if the system is behaving drastically different from what it usually does, then ensuring that it isn't able to take any kind of adverse action. That's what guardrails are for. It isn't able to take any adverse action that is in place is also a good way to make sure that you don't have a huge amount of negative impact on business. Coming to the last technical depth, um, um, sort of like the all the technical debt that essentially couldn't get classified in any of the other categories. So first one is like data testing. Essentially, your data changes over time. Sometimes your features may no longer be producing valid values. Sometimes the distribution might be changing from what you assume. So drift detection is a good way to mitigate for that. Reproducibility. Essentially, you want to be able to reproduce your model results so that A, it's helpful for debugging, and B, it's helpful for explaining why something happened the way it happened. So having good documentation is one way to ensure that you can reproduce whenever you need to. Seeding, so that you eliminate any kind of randomness, like you do the np.seed or pytorch seed. Wherever there could be any forms of randomness, try to eliminate it with seeding. And then versioning model parameters and features. Essentially, like different learning parameters you're using for your model, like hyper parameters that you're using. Create like, okay, in version 1, this is what we use. This is the set of features, like feature ABC is what we use. In version 2, these are the different hyperparameters used, and feature A and B is what you use. So making sure that you keep track of versions that went into production, and how and what those settings for those models were, is a good way to make sure that you can reproduce the results the model gave at a certain point in time, so that it's helpful for A, debugging, helpful for explaining to the business what happened and why something happened the way it happened. And the last one is a bit of a broad one, process management. This essentially happens when you're building systems, building ML systems in like live production, where multiple ML systems sort of interact with one another. So in those cases, it's really hard to figure out if something went wrong, what caused it to go wrong. So usually you spend multiple hours debugging and looking through the data to figure out, okay, this ML system interacted with this ML system in this way to create this kind of output. And yeah, it takes quite a few hours to figure out, okay, why did business see this kind of result. So this is sort of a cross team kind of effort, I feel, and it's sort of the hardest technical debt to address. But ideally, if you have some kind of visualization tool, some kind of debugging tool that works through these multiple ML models to figure out why a certain input gives a certain output, it does save a huge amount of time in terms of debugging, and a huge amount of time in terms of explaining to business why something happened the way it happened. But yeah, in my experience, this is like the hardest technical debt to resolve. So yeah, with that, I think we've covered pretty much all the key technical debts that pop up in a production system. For a quick break, just want to introduce one of the partners for BuildML, which is Automate Apply. If in case you're looking for a job, you'll notice that the hardest thing about a job service is essentially the application portion, primarily trying to figure out which all LinkedIn/Indeed boards to check out if a job application is actually suited for you, and then going through the process of creating an account, updating your resume, uploading your resume, making sure the resume is passed very well, and filling out the application. It takes about like an hour to 2 hours if you're actively searching for a job in the market, and it's a pretty draining hour to 2 hours. So Automate Apply is one of the services that actually automates this out for you pretty well. It's priced very reasonably, about 50% cheaper than anything else on the market. It's basically $1 for every two applications. It's a huge savings in time, and definitely recommend checking it out. I'll post the link towards the. I mean, if you use the code BuildML, you'll essentially get 10% off, and I'll post the link along with the video when we upload it onto YouTube. Cool. Now coming back to the presentation for the next paper, essentially production readiness. So we talked about all these different kinds of ML depth. We talked about all these different mitigation strategies, but it's hard to keep everything in your head, especially when you're going into productionizing an ML system. So that's where this paper comes in. It provides a checklist of things where you can work through one after another. And by the end of the checklist, you're essentially have sort of a good ML system. You don't need to solve every or account for every item in this checklist, like 4 in each category or even 3 in each category is a pretty solid ML system, I would say. So you need to hit at least 3 in every category. So, and that's what the rubric essentially boils down to. The rubric that the paper proposes is that you need to hit at least 3 in every category. So coming to the first kind of checklist, the feature and data tests. So starting with ensuring that you capture feature expectations in a schema. Primarily, this means that you understand what the feature values are going to look like, the distributions are going to look like, and you have encoded them in a way that you can test in the future that when, like as time goes on, you can keep testing this schema against the feature and making sure the feature hasn't drifted, essentially. It's another way of talking about drift detection basically. The next one is all features must be beneficial, like we talked about. Sometimes you have this kitchen sink approach of throwing all the features and seeing what the performance of the model looks like. So an approach that we use is leave one feature out validation. So you run it maybe like once a quarter, once a year, essentially to trim out any of the features that might not be as useful anymore, or maybe wasn't as useful at any point in time. So it's a good way of making sure that your feature set doesn't grow to like hundreds, 200s, or 300s. It keeps it like relevant and what gives you actual good performance. The next one is feature cost should make sense. Essentially, whenever you add a new feature, you might get an improvement in model performance, but is that improvement worth it? Uh, how you sort of assess that is by comparing the added training time, added inference time, the excess RAM usage that you're using, the excess cost of like maybe if you're on cloud, the excess cost. So you need to take that all of that into consideration when you're adding a feature, and not just look at the predictive performance. So all of it should make sense, and the sort of like what is worth will depend upon your team. But once you talk with your team, you sort of are able to figure out what delta you need to see to add this feature as a feature set into our feature set for a particular model. The next is data pipelines has proper privacy. Essentially, if you're dealing with PII data, protected features like gender, race, etc., make sure that the model isn't able to access them and they're sort of encoded in a proper way. Or especially for protected features, you're not using them or using their proxies in any manner. So this is more of an engineering task. Making sure that the access to these features is completely blocked and they're not used as a inference time in any way, shape, or form. And then sort of like making sure the protected classes, etc., protected features are treated as such. They're protected essentially and not used for in any way for inference. The last one is the second last one is new features can be added quickly. Essentially, if you want to test with a new feature, then you should be able to bringing the feature into your feature store fairly quickly, test it out, and productionize it fairly fast. And you should have systems in place to do that, like being able to run the model end to end, being able to see the impact of the metrics across all the metrics that you need to consider, and being able to launch quickly to A/B test. Like ideally, you want to be able to do all of this within like as minimum as 1 to 2 months, so that it's like 4 to 8 weeks. It might seem like a lot of time if you haven't like experienced this before, but usually including features takes a decent amount of time. And the last one is all input features are tested. Essentially, you should have unit testing for all your ETL to make sure that the ETL isn't breaking. So, and ensuring that the raw data is processed properly and the end results are stored. Make sure that all of that is unit tested essentially. And this is, in my experience, the only sort of unit testing you need in ML systems products. Coming to the next set of production readiness checklist guidelines, model development test. So ensure that every model undergoes a code review. Ensure that the metrics that you use when you're doing back testing correlates with the online metrics. Like if you're using precision recall when you're building the model, it sort of correlates with something like engagement or CTRs, like talking about like recommender systems. If you're using precision and recall and KSU metrics when you're building the model, improvement in them has to lead to improvement in CTR or conversion rates. So make sure that you use metrics that actually correlate. Then ensure that all hyperparameters are tuned. Ensure that the impact of model staleness is known. Like if your model isn't updated, like let's say you have a model that's trained every hour or trained every day. Let's say it misses one cycle, what would happen on the prediction results? You should know how much the prediction might drop, or if the prediction is actually staying stable. That should be sort of documented. Ensuring that a simpler model is not better, like maybe like once a month, it's always good to sort of see if a simple model with like a minimal set of features doesn't outperform your very complicated model. Because if it does, then you're probably doing something wrong, or something needs to be changed. So having that simple model in your production pipeline and letting it run is, I wouldn't say it's common practice. Like typically when you're developing a new version of the model, you test it out to make sure that your model is actually performing better. But this is something that the folks at Google seem to be recommending, but haven't seen it much in practice, I would say. Model quality is sufficient on all important slices. This is actually something that is done in practice. Making sure that different subsets of the data that you want to get good performance on, like if it's a classification task, for like or maybe a recommendation systems task for on Netflix. You want to make sure that different genres of movies are also getting recommended to make so that essentially you don't miss out on any particular subset of data, and you make sure that the model quality is sort of the same across different subsets of data. And the last one is the model is tested against bias. Like the predictor classes, like we mentioned before, gender, race. The model sort of treats them equally, provides predictions that aren't like starkly different if the gender or race is taken into account. Like since those classes, since those features are in use, since those features are essentially considered predicted, the performance on them should be relatively the same. Bias detection, sort of like bias detection, is becoming more and more relevant nowadays, and it's something that I've been seeing a implemented part of the production pipeline more and more often nowadays. Coming to the ML and infrastructure testing, um, these guidelines are fairly straightforward. Making sure training is reproducible in the sense that whatever results you get at time t, you should be able to get at time t plus 10, assuming the model hasn't changed. I mean, the model parameters hasn't changed. Second one, model specification is unit tested in the sense that whatever parameters you are providing to the model um, um, actually leads to the model working fine. Like let's say you change all the hyperparameters, the model shouldn't break. Then it shouldn't give like value errors or value warnings, any of those things. So running the model for one single gradient descent is one way to make sure that the model is performing well without throwing any errors. Then the ML whole pipeline is integration tested. Essentially, if you click start, the model should be able to take a random subsample of your data, do the training, store the model, run the inference, and provide predictions. And all of this should run smoothly without error. That's essentially an integration test. And that is actually quite common in like production systems. In like industry production systems, integration testing is quite common. Unit testing may not be as common, but integration testing is definitely common. Model quality is validated before serving. Again, making sure that whatever performance you're getting is comparable to the performance you've seen before. Again, a very common test. The next one, model allows to debug or observe the results of a simple sample. Essentially, you have tools like TensorFlow debugger, etc., to sort of figure out that. And yeah, making sure that's in place so that if in case you need it, you can always use it. The next is model is canary tested. Essentially, whatever model version A and model version B you have, if you want to deploy model version B as the sort of the new model version, you expose it to a certain small amount of traffic, like maybe 3%, while model A is getting 97% of the traffic. You make sure model B is performing as expected, and then slowly increase the traffic, like 3 to 9, 9 to 18, 18 to 50, 50 to 100, like that. You slowly increase the traffic so as to make sure that there are no adverse effects. And the last one, model can be rolled back. Like if in case there are any adverse effects, you should be able to roll back the entire traffic to maybe like model A. So those are like the ML infrastructure testing, that is a checklist that you need to hit. And again, you just need to hit like 3 to 4. In this, I would say the most important one is training is reproducible, ML is integration tested, canary tested, and rollback. These four are the most important. Debugging, if you can allow for it, that would be also a good one to have, I would say. Then the last sort of portion of the checklist, monitoring test for ML. The production, the last or the fourth and the, I would say the most important one and the most commonly implemented one in terms of production readiness, monitoring the ML system. So the first one, dependency changes are notified. Essentially, if your input features are going to be changed, their locations are going to be changed from X location to Y location, their they're going to be, the distribution is going to be altered or the features going to be normalized. Any of those changes that upstream data teams are going to be making, you should be notified about that. Data invariance, essentially, if the distribution changes naturally over time, then you should be notified about that. Typically, you use drift detection for it. Training and serving time features compute the same values. This usually happens when you have a feature that's coming in live, but when you're building the model to create those features, what you're doing is you're going and backfilling features. Like maybe you take 10-minute time slots and you try and assess what the feature would have looked like in those 10-minute time slots. So you're creating the feature when you're actually doing your training. So you don't have the feature coming in as it would during serving. So there might be slight differences. Ideally, there shouldn't be any differences. You should be able to backfill it in a proper way, but sometimes there are certain differences. And the idea is to make sure that this feature that you're backfilling and the feature that's being served at the inference time, they're about the same. The next is models are not too stale. Essentially, if you're retraining your model maybe every hour or every day, it is actually happening. You're keeping a track of the when the model is being updated, and if the model isn't updated, you're alerted. The next one is model is numerically stable, like especially vanishing gradients, exploding gradients, things like this. You're keeping a track of if during training any of this happens, you're notified. Or the parameter values, if it looks like they're getting extremely small or extremely large, you're notified. And the second last one, model does not have slow leakage in training speed, serving latency, etc. So as you go on, maybe like in your GCP, you have too many projects running. So now memory is a constraint. So the model training time is going down, or your GCS buckets aren't cleared. So now there are certain issues with like storing your data. All of these things you're keeping a track of, or have some kind of notification for, so that if in case it does happen, you're notified. And in terms of training speed, it's more like you keep a track of how much time from start to finish it took for the pipeline, and if that time is going up, you're essentially notified. And the last one, model does not experience reduction in prediction quality, the most important one. You're making sure that there is no drift, there is no drop in the accuracy or precision or recall or whatever metric that you're using for measuring the quality of your predictions. There's no drop in that. So you compare it with what training looked like, and maybe you compare it with just the prior validated run of the model, so that you can make sure that there is no gradual decline and there is no stark decline as well. So yeah, the monitoring aspect of the production readiness checklist is something that's very relatable. I feel like a lot of these are usually implemented in actual production systems, and this is sort of the one that you need to focus on the most, because you need to be notified as soon as something goes wrong. And with that, I think that's sort of the high level overview of the production readiness guidelines. I think we lost quite a few people, primarily because I think the topic was a bit more ML engineering related. But yeah, if anybody has any questions, we can go over them right now. But the key takeaways I would say from these two papers is sort of like working through this checklist. The checklist is fairly a solid one in terms of like what is the most important aspects of the checklist, or the most common ones I have come across. I'll definitely leave it in the notes, and the notes I'll share or link it in the video or when we upload it onto YouTube. And yeah, if in case you guys have any questions, feel free to drop them in the chat. I'll stop the recording now, and